What is going on, chemistry students? I am coming to you today by video to do a little bit of talking about nuclear chemistry. We are going to be discussing basically what nuclear chemistry actually is. We're going to be talking about some practical applications of nuclear chemistry in real life, as well as stuff that we can't do yet. And you're going to be learning all kinds of mostly fairly easy math-related things. But we're going to start off by taking a look at this question right here. Simple math problem. When does 2 plus 2 equal something that's not 4? Okay. Because, everything you've ever learned before in math tells you, well, hey, 2 plus 2, if you add it up right, should always come out to exactly 4. So what we're talking about here is actually a situation where we've got something that is going to be less than what we would expect to find. And that's what we're talking about when we talk about nuclear chemistry. So today, nuclear chem, we're going to talk about what a nuclide is. We're going to learn about something called mass defect and nuclear binding energy. And we're going to talk about nuclear stability and what it has to do with how big an atom's nucleus is. Now, if you recall, we have talked about one of the laws of conservation of matter is that matter cannot be created or destroyed. In a normal chemical reaction, let's say that I am burning hydrogen gas, I'm combining it with oxygen, and I'm making water. Well, I'm not actually making water. I'm taking hydrogen atoms and oxygen atoms that I already had. I am combining them in new and different ways, and there's energy involved, but I know that however many atoms I start off with is going to be equal to end up with. Well, that's always true unless you're talking about nuclear chemistry. Because it turns out that conservation of mass is not always really a thing. For starters, just a little bit of terminology. What we have talked about before being protons and neutrons, the particles that make up an atom's nucleus, we can collectively call them something called nucleons. Okay, and the nucleon part comes from the fact that it's a part that's found in the nucleus. We can also refer to an atom as something called a nuclide. Again, having to do with nucleus, because if you look at an atom, a lot of its chemical behavior depends on its electrons. We're going to be focusing on the nucleus of that atom, and so it's really going to be more important for us to look and see what's going on with the protons and with the neutrons. We've talked before about when you've got a chemical symbol like this, the 1 or 2 letter symbol comes from the periodic table. It usually comes from an element's Latin name. The top number is the mass of that element, and the bottom number is the atomic number, or the number of protons. We can refer to something like this particular atom of radium, we can call it radium-228. And the 228 comes from the fact that it has a total mass of 228, and that's because it has a total of 228 particles in its nucleus. Now, just kind of as a refresher, if I've got radium-228 and had an atomic number of 88, that means that of that 228, I've got 88 protons. The rest of the mass is made up of neutrons. And I can find that simply by taking the total mass minus the mass of the protons. So that would be 228 minus 88. So in other words, in this particular nucleus of radium, or this radium nuclide, we have 140 neutrons. And so altogether, we say that we have 228 nucleons. Okay? It's nothing new, it's just a new name for something you've already known about for quite a while. Okay, so no need to panic there. Now, here's an interesting thing. When you take when you take protons and neutrons and you put them together in order to make up a atomic nucleus, the mass of the nucleus is different from the total mass of all of its protons and neutrons. Okay? In other words, if we've got, say here, this atom of helium has a total mass of 4. It's made up of 2 protons and 2 neutrons. 4 minus 2 is 2. If I was to take the masses of those protons individually and add them to the neutrons, I would have a mass of 4.032979 AMU. AMU, remember, stands for atomic mass units. But if I actually take the mass of a helium nucleus, the mass I get is 4.002602, which means if you look at these two numbers, the difference is 0.030377 AMU. Now, is that a lot? No, it's not. Because remember, an AMU, or an atomic mass unit, that's about equal to the mass of a single proton or a single neutron. Pretty close. But it's not exact. And so you have to wonder, well, if I take 2 protons and 2 neutrons and I stick them together and I make this nucleus, where does that extra mass go? And that missing mass, that mass that seems to disappear, is referred to as a mass defect, okay? Not defective in as much as, hey, it's falling apart, but defect here means, hey, we're expecting there to be more mass than there actually is. And it's a really interesting answer you get to that question of where did that mass go? A fellow named Albert Einstein, you might have heard of him, came up with an equation. You might have heard of it. E equals mc squared. In fact, it's probably the single most famous equation in all of science. Let's talk about that for a minute. Oh, I think my webcam froze. Good times. If I have E equals mc squared, here's what that refers to. E, you might have been able to guess, is energy. M is mass. Now C is a constant. C is the speed of light in a vacuum. Now the speed of light in a vacuum is 3 times 10 to the 8th meters per second. Okay? So we're talking, if you imagine a meter is about the size of a yard, then light can go about this many, slightly more than yards in any given second. If I was to write that out, I'd put 8 zeros on the end of this. And so we're talking roughly 300 million meters per second. It's a really big number. And so you take that number and you square it, meaning you multiply it by itself, you make an even more ridiculously big number, and then you take all of that and you multiply it by a certain mass. What that tells us is when I take protons and neutrons and I put them together and I make a bigger nucleus, that missing mass gets turned into energy. And it doesn't just get turned into a little bit of energy, it gets turned into, the scientific term for this is a buttload. Okay, there's a buttload of energy that happens whenever mass turns into energy. And it's all according to Einstein's E equals mc squared equation right there. Now that's super important. What that means is anytime that an atom gets put together, some of that mass gets turned into energy, and that energy that's released is something called the nuclear binding energy. And it's a lot. Okay? The larger the amount of nuclear binding energy, the more stable a nucleus tends to be. That's going to be really, really important when we start talking about applications of nuclear energy. So if you want to look here at how much energy we get right here. Okay, so right here is the mass defect whenever you take that's the mass defect we saw a couple slides ago when you make an atom of helium from its protons and its neutrons. Then if I change that into kilograms, that's an even tinier number. That's like 5 times 10 to the negative 29th kilograms. That's not a very big amount. But then whenever I run it through E equals mc squared, I'm going to multiply that mass in kilograms times 3 times 10 to the 8th meters per second squared. And I end up with 4.54 times 10 to the negative 12th joules. Now, you remember joules as being a unit of energy. We talked about it when we talked about thermochemistry. That doesn't sound like an awful lot, but keep in mind that atoms are very, very tiny. And if you're having, atoms being made, or in some cases being broken apart, what's happening is that a lot of atoms are going through this, not just one or two. And so a lot of energy ends up being released. And that's where we get nuclear energy from. So what you see here on this slide is an example of a nuclear reaction. In this case, let's talk about what's going on. We've got a nuclide of beryllium-9. It is going to smash into a nuclide of helium-4. They're going to smack into each other. And on the other side of the equation, what they're going to do is those two smaller nuclei are going to stick together and make an even bigger nucleus. They're going to make a nucleus of carbon-12. Now, when that happens, energy is released. But let me show you what else is happening. We also get this right here. That little n right there is a neutron. You can tell it's a neutron because it has a mass of 1, but it does not have any protons. It has a charge of 0. Now, this right here is a balanced nuclear reaction. Now, the good news is that balancing nuclear reactions is a lot easier than balancing just regular old chemical reactions. You have to be sure that the total mass, which is your top numbers, is the same on both sides. And if you look here, 9 plus 4 makes 13. 12 plus 1 also makes 13. You also look to make sure that the charges, or the total number of positive charges, total number of protons, is balanced on the bottom. So we've got 4 plus 2, that makes 6. We have 6 plus 0, that also makes 6. So we can verify that this is a balanced nuclear reaction. The thing is, atoms can turn into other kinds of atoms. I don't know if I've ever mentioned this or not. If you remember way back in the day before chemistry was even a thing, there was a group of these folks called alchemists. And what alchemists would do is they would try and take cheap stuff like lead or other, less desirable metals, and they would try and find some way of turning them into gold. They figured they could get filthy stinking rich and maybe get a girlfriend if they could figure out how to do this. They never were able to do it, and for a long time people thought, well, that's because it's impossible for an element to turn into another kind of element, except it happens all the time. When one kind of elements turn into another kind of element, that's something called a transmutation. The number of protons in that nucleus changes. Sometimes it happens because other pieces stick to it. Sometimes it happens because a nucleus is just so big and unstable, it starts falling apart. And so it starts losing pieces of itself. It turns into a totally different element. That's going to be a nuclear reaction, and that's what we're going to be talking about quite a bit of. Again, if you're going to be balancing a nuclear reaction, you want to check that the total mass on both sides adds up the same, and you want to check that the total atomic numbers, the lower numbers, the charges, add up to the same. So I've gone through a lot of things and crossed off a lot of stuff on this slide because we're really only going to be concerned with a couple of ways that an atom goes through a nuclear change. We're going to be talking about something called beta particles and something called alpha particles, and we'll talk about that more, so I'm going to skip past this slide. If you had to balance out this nuclear reaction, what we've got right here is we've got an atom of polonium-212. Now, it's going to fall apart. One of the things it's going to fall apart into is this helium nucleus right here, which has a mass of 4 and a charge of 2. We want to see what's left over after it's done. To find that, we take 212 minus 4. We'd end up with 208. I'm just going to jot this on my paper real quick. We would do 84 minus 2, and that's going to give us a particle that has a charge or an atomic number of 82. So what we're talking about is this nuclide right here, and all we have to do is look up element number 82 on a periodic table, and I'm going to cheat and do that real quick. Just type element 82. Element 82 is lead, so I would put the symbol for lead, not peanut butter, and that would be what that atom of radium has transmutated into. Would be an atom of lead 208, or a nuclide of lead 208. Okay, let's pick up the space here just a little bit. Okay, lead 208, that's balanced. I'm going to talk just a little bit about radioactive decay and nuclear radiation. Okay. So if you've got a great big fat nucleus that is unstable, it will tend to fall apart. And we're not talking about little atoms like, hydrogen or oxygen or carbon, although some of them are unstable and some of them do fall apart. We're talking about big Chungus atoms. We're talking about like uranium and polonium and plutonium and americium and all the other ones that are down at the bottom of the periodic table, the great big dudes. Well, those dudes have big unstable nuclei. They've got a whole bunch of protons all crammed real close together, and they're all wanting to push away from each other, and every once in a while they fall apart. And we're going to be looking at 3 different ways that atoms go through radioactive decay. And when they go through radioactive decay, it means that pieces of them are going to fall off, and then those pieces are going to go flying out and form what's called nuclear radiation. Now, you have to be careful of nuclear radiation because nuclear radiation is generally bad for living cells. It can tear living cells up. It can rip up your DNA. It can kill itself. It can give you cancer, all kinds of bad stuff. So let's talk about types of radioactive decay. The first type we're going to talk about is something called an alpha particle. Okay? An alpha particle, which has this symbol right here. It looks a little bit like a fish. That's the Greek letter alpha. It's the first letter of the Greek alphabet. That's where we get the name alphabet from. An alpha particle is just a helium nucleus. It has a mass of 4, and it has a charge of positive 2. So it's like a big fat nucleus spits out a helium nucleus from itself. You saw this in the example a minute ago with the big polonium nucleus spitting out a helium nucleus. Well, it's spitting out an alpha particle. An alpha particle is the least dangerous kind of radioactive decay. It's the least dangerous kind of nuclear radiation. Because it's big, it tends to move fairly slowly. You can stop an alpha particle with a few sheets of paper. So if you're going to be working around alpha radiation, if you put on a paper hat, it ought to protect your brain, you'll be just fine. Now beta decay, something a little bit different. Now a beta particle, symbolized with this little B that looks like he's got toilet paper stuck to his shoe, that's the Greek letter beta, is actually an electron. Now, I want to talk about this because this is strange. You're like, Mr. King, I thought we were talking about what's going on in the nucleus. We aren't talking about electrons. And you are right. So I want to show you an example of something like this. Let's say that I've got something like lead 208, okay? Now this lead 208 is going to go through beta decay, meaning it's going to get rid of a beta particle. Now a beta particle, since it's an electron, it has no mass, and it has a charge of -1. And I can either symbolize it by doing the Greek letter beta like that. I could also symbolize it with a little e for electron. Now, if this lead nucleus got rid of this beta particle, what would be left over? Well, let's balance our masses and our charges. The total mass over here is 208. So 208 minus 0 would still be 208. Now, the total charge on this side is positive 82. Now, 82 minus negative 1 is like adding a positive 1, so it would have a charge of 83. And so what's going on here is that we no longer have lead, which is element number 82. We have element number 83, which is bismuth. Bismuth is an active ingredient in Pepto-Bismol, that nasty pink stuff you drink to try and keep you from throwing up. It usually is so gross it makes you throw up anyway. Bismuth has an atomic number of 83. Now, if you look to see what happened before, we only had 82 protons, and now all of a sudden we've got 83 protons. Where did that other proton come from? And the mass of the atom didn't change. Well, here's what happened, folks. Somewhere inside of this nucleus, there was a neutron, okay? And this neutron was just sitting there chilling, minding his own business, having a charge of 0. And this neutron goes patooey, like that. And what he is patooing out is an electron. He is patooing out a beta particle. Now, when he spits out a negative charge, because he had a charge of 0 to start with, when he spits that negative charge out, he becomes positive. And you know what you call a particle that's the size of a neutron that's positive? That's right. You call him a proton. So literally what's happening is that a neutron somewhere in that nucleus is spitting out an electron. It's spitting out a beta particle, and it is changing from a neutron, which has no charge, into a proton, which has a positive charge. We're talking crazy, I know, but it's nuclear chemistry. Crazy stuff happens. So again, beta particles. Now, beta radiation is a little more dangerous. It moves a little bit faster. It's a smaller particle than an alpha particle. And so beta radiation, you can protect yourself by a few millimeters of something heavy like lead. So if you're working around beta radiation, usually wearing something like a lead vest or a lead suit, you know, kind of like they put on you when you go to get your x-rays taken at the dentist's office. And that's because one of the things they're using for those x-rays is a source of beta particles. They're using some kind of radioactive substance that's giving off beta particles. And so you can protect yourself. They're a little more dangerous, but not super dangerous. We're not going to talk about positrons because I don't care. We're not going to talk about K-capture because I don't care. You get into college and you want to talk about this, that's fine. We are going to talk about gamma radiation. Now, unfortunately, gamma radiation is not going to turn you into a big green angry guy who likes to smash things and run around without a shirt on, okay? That's the comics. Real gamma radiation, if it gives you a superpower, that superpower is called cancer, and it's got another superpower called, painful death. Gamma radiation does not have mass. It is pure energy. And gamma rays are very, very high energy electromagnetic waves. They're up here. They've got more energy than visible light. They've got more energy than UV, and you know that UV is dangerous. X-rays are dangerous. That's why you wear the stuff. Gamma rays are some of the most dangerous radiation of all. If you're going to be working around gamma rays, you want to be sure that there is several feet of concrete between you and those gamma particles because they will tear you up. Gamma rays are symbolized. This looks like a letter Y. It's actually a Greek letter gamma, which looks a little bit like a Y, but not perfectly like a Y. We're not going to be doing very much math with these. We're just going to mention that they're a thing and they can kill you. So, don't mess with them. So, just in summary, alpha particles, they're like a helium nucleus. They've got a mass of 4, a charge of 2. Beta particles have a mass of 0 or almost 0, charge of -1. Gamma rays have no charge and no mass, but they are very, very heavy on the death scale, okay? They will mess you up, okay? I don't think I'm going to talk about half-life just yet. I may save half-life for a coming week, but we'll skip through this slide here. It's an interesting thing to read up on, but we're not going to get into it just at the moment. Skip through this. All right, now we are going to talk a little bit about decay series, because typically whenever an atom is unstable and it goes through radioactive decay, it will turn into another unstable atom. That unstable atom will go through more radioactive decay to turn into another unstable atom, and it will do this several times until it reaches something that is stable, something that's not going to fall apart. So this is a little bit unusual. Take a look here. The way that you read this, we're going to start with high atomic number. Wow, go back. We're going to start with high atomic number and a high mass number. So we're starting up here with this atom of uranium. This atom of uranium is going to go through an alpha decay. It's going to become an atom of thorium. Thorium will go through 2 beta decays to become proactinium and uranium. Then it will go through another alpha decay to become thorium, and another alpha decay to become radium, then another alpha decay to become radon. We'll go through another alpha decay to become polonium. Now at this point, it could either go through a beta decay and then work its way down this way, or it could go through another alpha decay. But you see, each time that you're changing from circle to circle and following an arrow, it's either following an alpha emission, which means that its atomic number and its mass gets smaller, or it's following a beta emission, which means that its mass doesn't change, but it's getting a greater atomic number because those neutrons are turning into protons. And so at the very end of all of that, you end up with this stable nuclide of lead. I believe that's lead 206. I can't quite see. Oh, yeah, it's 206 right there. Lead 206 is stable. It doesn't turn into anything else. It just remains lead. Now, the thing about this is that depending on which of these reactions you're looking at, some of them happen very, very quickly. Some of them can take thousands or even tens of thousands of years, okay? Because some of these nuclides are more stable than others. Some of them, like if you look here, this one, this polonium-218, it tends to change to something else in about 3 minutes. This astatine-218 only hangs around for a matter of seconds before it turns into something else. If you got something up here like this thorium-230, it can hang out for 7.5 times 10 to the, I think that says 6th. So that can hang out for like 7.5 million years. Okay, much more stable than some of these guys down here. I think I've really said enough as far as introductory nuclear stuff. There's more in the slideshow that we may come back to and talk about, but I feel like this is probably running a little bit long, so I'm going to go ahead and wind it up. Now, I will point out that there are a couple assignments that will go with this. I've got Zoomcasts, and I'll be videoing those that go with each of those 2 assignments. One is on practicing writing and balancing nuclear equations. We'll be doing that Wednesday morning. Another one is a simulation, which we're not going to be doing with PhET. We're going to be doing it using some smaller stuff like marbles or Legos or toothpicks or something like that. And I've got that scheduled for Thursday afternoon at 1 o'clock. So I'll be here during most of my regular help desk hours if you have any questions about those. But in the meantime, try and absorb this. Take a look at those papers and see what you can figure out. And I'll be talking to you soon.